So before we talked about what condition variables were, we talked about a human-known use of condition variables related to delivering pizza. I talked about the guarded suspension pattern, and I gave you some examples of common use cases for using conditions, and talked about how they're always used in loops and things like that. What we're going to do now is talk more about the structure and functionality of the Java ConditionObject class, which is a very interesting and somewhat complicated class to understand its innards, but the actual use case is fairly simple. So ConditionObject is the way that Java provides an implementation of the condition variable abstraction we talked about before. And this particular class implements the condition interface, which is one of the core lock interfaces that are available. And internally, it uses that abstract queued synchronizer framework that the ReentrantLock and semaphore used in order to be able to manage some of the details of how things work. In fact, interestingly enough, condition objects are actually implemented, I believe they're implemented as a nested class inside the abstract queued synchronizer class, which is kind of interesting. Condition objects, if you recall when we talked last time, we talked about how condition objects provided this wait set or wait queue of nodes. So you basically have a queue of waiting nodes where each node corresponds to a thread. And this enables the set of threads, which are the wait set we talked about before when we talked about condition variables, to coordinate their interactions, basically by signaling or waiting for things to happen that make conditions perhaps more to their liking. So that's the secret sauce behind all this stuff. So you'll have a bunch of threads where each thread has a node. And essentially, the set of threads use the condition objects to dictate the order and the conditions under which they get a chance to run. So we'll show some examples to make this more clear, but that's the kind of a high level. Something important to remember, really, really important to remember, a condition object is always used with a lock. And by and large, it's used with a reentrant lock. So a condition object always has a lock, typically a reentrant lock, that's associated with it. In fact, it's more than just associated, it's actually created, the condition object is created by a factory method in the ReentrantLock class. And this lock is used to protect the shared state in the condition expression to make sure it's not corrupted by multiple threads that are trying to access that state at the same time. So if you recall, we talked before about some things like, the array blocking queue, where we've got fields like the count, and we've got fields like the next index to put something, or the next index to take something, and so on. And that's all mutable state that needs to be protected from concurrent access. And so this lock is used to do that. By the way, does anybody know what this famous scene is? Very good, very good. Margaret gets 10 points. Good job. 10 points to Gryffindor. Well, that's the wrong metaphor. 10 points to the House of Theoden. How about that? Yeah, so that's an example of protecting the state. Actually, literally protecting the state, because the king was the head of the state. So the way that we do this is the new condition factory method. That's the thing that returns the appropriate condition object. Both condition object and ReentrantLock have internal queues. And this is a little bit confusing at first, because these queues are used for two different things. This queue over here that the ReentrantLock queue has is called the entrance queue, and this queue over here is called the wait queue. And you'll see when we talk later about Java monitor objects that Java monitor objects, built-in monitor objects, also have an entrance queue and a wait queue. So condition objects are much the same kind of thing. So the ReentrantLock's queue is used to queue up the threads that are waiting to get the lock, and the condition object's queue is used to queue up threads waiting for some condition or conditions to become true. So they're waiting for two different kinds of things. This is waiting to get access, and this is waiting to do something once you get inside the guarded suspension region. Once you're inside that critical section, this is going to be used to wait for something to happen. So I'm trying to think of some examples that might be intuitive for why you have two queues. So let's say that you want to go to a nightclub, right? So you want to go to let's say you want to go to a really popular nightclub, so there's always a line of people waiting to get in. So the entrance queue is kind of like the queue of people waiting to get into the nightclub. And then once you get into the night, by the way, not that I'm advocating going to nightclubs if you're not old enough to drink, but maybe it's a nightclub that just plays music or something like that. So once you're into the nightclub, then there will be other queues to get various things, right? You might have a queue to go to the restroom, you might have a queue to get a drink, you might have a queue to play something, play pool, or whatever you're going to do once you get into the club. So that's kind of the idea. You have a wait queue to get to the specific resource you want, and you've got an entrance queue to get in the first place. And so that's why we have two different queues. So when you have user-defined Java objects like array blocking queue, you can have multiple condition objects, which I'm going to call COs for short, because condition object is a bit of a mouthful. So for example, our array blocking queue, whose implementation we'll look at in a second, has two conditions, not empty and not full. And as you might expect, they're used for threads that want to wait for the queue to be not empty and for threads that want to wait for the queue to be not full. This is very important. Multiple condition objects in a given user-defined Java object enable more sophisticated and efficient ways to coordinate multiple threads. And the reason for that is that you can have multiple wait sets per user object that share this single lock, but can be notified on different conditions. Yes, Andrew. Yeah. So the ReentrantLock is kind of like getting into the nightclub. It's like queuing up to even get in the first place. And then once you're inside, you wait for certain things. You wait for a table. You might wait for a drink. You might wait for the restroom. There's a bunch of things. Those are specific things. The analogy breaks down a little bit, but it gives you the idea that there's real-life examples where you have multiple ways, multiple places to wait. I guess you could use airports too, right? You have a queue of people waiting to go through the TSA line, and then once you get there, you have queues to get food, queues to board the plane. So there's different levels of queues. Java's built-in monitor objects, which we'll talk about in more detail later, only support one monitor condition. So there's only a single wait queue, no matter how many different conditions you have to wait on. And this is really the fundamental flaw with built-in monitor objects. They really are very deficient. And we'll talk more about that later. Why this is a problem is because you end up having to notify everybody when you're waiting for stuff to change in monitor objects, built-in monitor objects. And so you end up waking up lots of extra threads because they all have to go and check this condition with a single condition. And we'll talk more about that later. That leads to something called the thundering herd problem. Yeah? There could be, but if that's the case, you have to program it so that that is correct. So, for example, if you could use, as you will find out very shortly, you will use condition objects to implement a semaphore. So that would be an example where you could actually have two threads, both of whose condition expressions would be met, because what they're checking for is whether or not the count of the semaphore is greater than 0. So let's say, for sake of argument, the count of the semaphore was 4. Two threads come in. They are able to acquire the lock. They check, aha, the thing is still greater than 0. I get to go. The other guy goes, oh, the thing's greater than 0. I get to go. Now, they won't actually go at exactly the same time because the lock is still used to serialize access to that shared state. But you could end up with condition objects discovering that the condition was true and continuing to make progress, depending on what the condition was. And in that case, as long as it's greater than 0, threads can go forward. But yeah, that's a great question. OK, so that was just a quick overview of the structure and functionality of Java ConditionObject.